Hello and welcome to a new video presented by Teleskop-Service. My name is Thorsten, and in this video I want to talk about filters in astronomy. So first let me do some theory here. Why we need filters? So when we take a look on the light spectra, which is this one here, you see on the one side the ultraviolet light over the visible range into the infrared light. So all the objects we want to observe are somewhere in that range. But unfortunately in that range are also all the other light sources. So maybe you want to select specific portions of the light, or you want to block out unwanted light. So for example, light pollution is one big issue that you may want to reduce. Then you can use filters. You use filters to block specific portions and therefore enhance other portions of the light. So that was a very simple approach in all these filter topics. So let me dive a bit more into details. Maybe we start with visual observing. When you want to observe some object in the sky visually, you can use filters to enhance the contrast. That is one approach. For example, when you do planetary observing, then you can put in a color filter with a specific color to enhance cloud structures or to enhance specific things on planet surfaces. For example, a red filter is good for Mars, or a blue filter for Jupiter to see the clouds even better. So there are many different ways to improve that visual observing. And also for nebulas, filters are usable. For example, for visual observing, an O3 filter is usable for emission nebulas. And maybe the third thing is just a block filter. Yeah, normally you don't want to block any of the light. But for example, when you observe the moon, which is pretty bright, especially in a telescope, then you want to use a neutral density filter to reduce the amount of light, to reduce that glow, that glare of the moonlight. So visual observing, definitely an interesting topic for filters, but if you go real into astronomy, then you'd also do astrophotography, and then filters play a crucial role. So the first approach is to use simple color filters. Especially red, green and blue filters. For example, here we have a blue filter. When using a monochrome camera, then you can use these three filters, red, green and blue, to capture these single bands of color. And you get grayscale images, of course, but then you can combine them into a color image, a RGB color image. That is one major approach in monochrome astrophotography. This is also the thing that your color camera does within the sensor itself. So on the pixels on the sensor, there are color filters applied, red, green and blue, and the sensor and the electronics calculate that image by themselves. When using a monochrome camera, you have all the options. You have the full resolution, which is pretty cool. You don't need to interpolate that biomatrix. So you have the full resolution, and you can also fine-tune your filters that you use. Maybe you want to exclude some bands, or you want to use infrared filters in addition to the red filter or something like that. So you have all the options. That is pretty cool using these filters. But that's only the first approach. You can go even further. The next thing you stumble across is light pollution. So that's definitely a thing as an astrophotographer you have heard about. And thankfully, the street light shines in specific wavelengths, especially for sodium lamps. That is a yellow-orange light. And you can use light blocking filters to block out these specific wavelengths. They are called light pollution filters. for example, the UHC, CLS, L Pro, you name it, how they're called, all these filters are possible to reduce the light pollution. So they can't do magic in some way, to be honest. So you can block that light pollution, but all the other wavelengths are also affected, especially nowadays with LED lamps. That's a big issue because LEDs are emitting light in other bands too, not only in that yellow and orange. So then light pollution filters are not working that good anymore. The only way to overcome this is to find a dark spot, a dark site somewhere near you. There's one way you can try, and this is with narrowband filters. So especially emission nebulas emitting their light in specific wavelengths. For example, the most prominent in the night sky is the hydrogen alpha line, which is red, a very deep red, and this is very prominent in the night sky. When you're using H-alpha filter in front of your camera, you can also, under light polluted skies, you can capture stunning images of nebulas. With narrowband filters you can also use two other ones. The second one is the O3, which is a blue light. Also that O3 line is very prominent in the night sky, so you can capture many objects with that. And the third one is the sulfur line. So this is an even deeper red than the H-alpha, and this is also very interesting because when you combine these three colors, you can map them to RG and B and then create a color image again. This is then of course a false color image, but pretty cool to have. You can then tune the colors in any way you want. There are many ways and options to do it. You can combine it SHO or HOS or whatever you want. That way is very common over the last time. It was first very prominently used by the Hubble Space Telescope. So this is also why this is called the Hubble palette when mapping these three colors. Some more words to narrowband filters. They are available in different bandpath width. So that's pretty important to know. The narrower that bandpath is, the more contrasty your image will be. So when you use, for example, a 3 nanometer filter, only the very H-alpha portion is allowed to pass through that filter. That means you need long integration times or a very fast scope, a very fast setup. On the other hand, there are broader filters available. For example, one of the bigger band passes is 12 nanometers wide. Then it captures more of the surrounding light, so you don't need that much integration time. But it's also not that with that high contrast. I talked about monochrome cameras. You can also use especially the light pollution filters with color cameras, of course. So when you have an OSC camera, you can put a light pollution filter in front. It will slightly change the colors of the object, but not that much. Most of the time it's not that much, so you can easily overcome that color shifting effect in post-processing. And as mentioned, there are many different filters available. I would recommend look at the spectra of the filter, of that bandpass spectra, to see what these filters can do for you. So what portions are blocked, which portions will be passed. Now let's check out what filters you need. Therefore we have to start with the filter size. You see it here on my desk. I have different filters here. We start with this very small one. This is a 1¼ inch filter. This is pretty common, especially for visual observing, because you can screw in these filters directly into your eyepiece, put your eyepiece back in the telescope, and then you can observe with that. This is the way to do it for planetary observing or nebula observing. So then there is a filter size of 36 millimeters, which is a common standard, 36 millimeters, but then unmounted. That means you don't have that black mounting ring around the filter, you have just a plain glass plate. That has some advantages, so you can build very thin filter setups, but also the disadvantage that you have to be very careful when mounting the filters. You should wear cotton gloves or something like that to not bring fingerprints onto that filter. That will really annoy you, so please be very careful with them. The next biggest size is the 2-inch mounted version, like this one here. So it's roughly 50 millimeter in diameter with that 2-inch thread here. So you can also screw them into a 2-inch eyepiece and do visual observing with these filters. That's the way to go. They are also available as unmounted filters with the same approach to build very thin setups, very thin filter setups with unmounted filters. One very special size are square filters. Here you see a clear glass square filter, 50 millimeter, so 50 millimeter square. This is especially for very large sensors a good approach, and they are used very effectively because you have a somehow square sensor format and a square filter, so that's fitting pretty well, but it's only needed for very big sensors, full frame camera and above. And last but not least, a very special kind of filter design, which is a so-called clip filter. So this is an APS-C clip filter. The idea is to put this filter in your color camera, especially a DSLR or DSLM. So you put this filter into your camera housing in between the sensor and the lens, and it stays there until you remove it, so it's independent from your lens. You have this filter always applied. That can be a correction filter if you have a modified camera to correct your white balance, or it can also be a light pollution filter like this one, but in this clip format. So that's a pretty good approach for DSLR and DSLM camera users. They are available for Canon, of course, and also for other brands. These filters are available. Just check out the shop, then you will find them if this is an approach for you. Alright, now we talked pretty much about different filters, but now how to apply them, how to use them. So there are, of course, as usual, many options. The first one I already mentioned, screwing in the filter into your eyepiece. That's for visual observing. And in theory, you can also screw in the filter. For example, let me just quickly grab this one here. You can screw also the filter into your camera. So that is basically working, especially if you have a, let's say, a common filter like an UV IR cut filter or a light pollution filter. That may be okay to just put it in front of your camera or in front of the corrector and have it there in place. If you always use this filter, that's okay, no worries about that. But normally you want to have the option to exchange the filter, because when you change that screw-in filter, you have to redo your flat frames and you have to first disassemble something. So this is normally not what you want. There are many more convenient ways. And the first one is the so-called filter drawer. So you have that housing here. This is just one example that we offer. They are also available in different sizes, different shapes, and very important, different threads. So for example, this one here has an M48 thread, which is common for nearly all correctors, all, let's say, reducers and correctors. And on the other side, there's a T thread, which is common for cameras and also some other equipment. So that means you can screw in this filter drawer directly onto your telescope, put on a camera here with an extender, and then that's it. That's just the way to go. And what you then have is the drawer itself, so that filter holder here, which comes into that housing. And this is magnetically locked, so don't worry, that can't fall off. And here you put in your filter. And now here you see you are a bit limited in the selection of the filter, so it may not be too thick. If it's too thick, then it will not fit into that housing anymore, so you have to check this out. Here's enough clearance, at least 2 more millimeters of clearance here, no problem. But there are also thicker filters available and they may create problems. So filter drawer is perfect if you rarely change filters, but you have to. For example, you change a UV IR cut filter with a light pollution filter, then you need 2 of these holders, and then just prepare the holder with the filter, and then you can quickly exchange them. On the other side of the range there are the so-called filter wheels. So especially when you do, let's say, more professional astrophotography. For example, you want to observe the whole night without touching the telescope. First of all, a filter wheel is normally used with monochrome cameras. Sure, you can think of some configuration where you use filter wheel with a color camera, but that's very rarely used, very seldom. So the normal way is to use a monochrome camera and a filter wheel. And with that you have many advantages. The first one is, the idea behind is that you can change the filters automatically, especially with a computer, with your imaging control software. You can change filters and therefore create sequences of images. You can capture RGB, luminance, whatever you want, within one session without touching the telescope at all. And that's pretty cool, and that's how it is used nowadays with filter wheels. Let's have a look inside. So here in this specific version I have of access guider mounted directly to the filter wheel with a small camera. And here in the inside you see it is a 7-position filter wheel with 2-inch filters. So it's the same size as these ones here. And here are LRGB SHO mounted. So 7 positions full, and I can create true color images and narrowband false color images with these filters. Here we have a little electronic, USB connection and a stepper motor. That's the most important part. And the stepper motor rotates that central wheel here until your specific filter is in front of the camera, and then you can just capture images, and then it's switched to the next filter, capture again, and so on and on. The cool thing here is everything here is sealed, tightly sealed, so no dust is coming in. Especially if you have a corrector here in front of that filter wheel, then everything is closed, no dust issues at all. Okay, that was a very quick and compressed overview of filters. There's one more thing that I want to talk about, and this is choosing the proper size and the proper filters. So the first question is how to decide what filter size should you use. Well, it depends first on the size of your camera sensor. Is it that small? Is it an APS-C? Is it a full frame sensor? That's the first thing, and also on the focal ratio of your telescope. Maybe you have a very slow one in terms of focal ratio, like a Schmidt-Cassegrain, or maybe you have a fast optimized Newtonian, then you have to use different filters. To calculate that, there are formulas available. I will also put a link in the description below to a website where I found a pretty interesting calculator. So we are not affiliated with them, just randomly found on the internet. There are also formulas available where you can calculate the vignetting. And this is exactly the problem that you have. When you use a filter and a sensor, it will not in the first place will not block completely the light. It will vignette the light. It will obstruct it in the corners, and up to a certain amount of vignetting you can calibrate this out with flat frames. This is one of the reasons why you should use flat frames, to calibrate that vignetting away. If the difference is too high, then these corners are just black. Then also no calibration works, no flat frames will work. The images are still usable in the center, but then you have to crop heavily. So that's not what I would recommend. I would always recommend using proper or larger filter sizes when choosing a setup, because it is just annoying always to crop out the frame and the interesting objects. So the next filter size that was available is the 36mm. 36mm is indeed usable with an APS-C sensor. If you use a very compact design, like it is available from QHY or ZWO with their filter wheel, where the filter wheel is very near to the sensor, then also 36mm are working, and this will create a super compact setup. I really love them. But it's definitely on a limit. If you want to put the filter more away from the camera or use a bigger sensor, then I would recommend always 2-inch filters. You can use 2-inch filters also with full frame cameras. That is also working, let's say up to or down to f5 focal ratio. If it is faster, then even that may be a problem, and you may switch to these square filters that I showed you before. Okay, so we are at the end of this video here, a very compact and compressed overview about filters. I hope you liked it. If you have further questions, as usual, feel free to drop a comment below the video. We would really appreciate to answer your questions. And maybe you want to share some photos that you captured with filters. We are also interested in that. Thank you very much. See you next time. Bye bye.